Yeah, no, we have 2 more. That's good. Let me see.
Recording in progress.
Okay, so the recording started already. So, Katharina, you are the boss, so you decide. Yep. You decide when you want to start, but I think any time, you can wait a minute. It's completely fine with me.
So yeah, like suggested, we can wait 1 minute and then.
Yeah. So it's just you decide as you like it, and how you do it with the timing also, and if you want to give warning or.
Yeah, actually, would you like a warning, Luis, or?
I have the time here, so it's fine. So I will time it for 25 minutes, such that there are a few minutes for questions.
Good.
That's excellent.
Okay. So I think we can start. So it is my pleasure to introduce Luis Silva, that will give a talk on impact of classical and quantum radiation reaction on collective plasma dynamics. And so, Luis, please, the floor is yours.
Okay, thank you very much for the introduction, and particularly thank you very much for the organizers, not only for setting up such a great program, but also for the invitation. So today I'm going to tell you about something which kind of takes us back to the fundamentals of classical and quantum radiation reaction, and in particular how they impact the collective plasma dynamics. So this is work that has been done mostly by my PhD student Pablo Bilbao, also in collaboration with Thales Silva and Ricardo Fonseca, and we've had very fruitful discussions with many people, in particular with Bob Bingham. So my plan here is to give you an example of what we call extreme plasma physics, which is this when plasma physics is modified by additional physical effects. There is a nice paper by Dmitry Uzdensky that and co-authors that introduces the concept for extreme plasma astrophysics, but you can see that we are talking about extreme plasma physics whenever there are exotic effects that you don't get in a traditional plasma physics that play an important role. And if you go here through the list, I'm going to focus here on radiation reaction effects. So one of the impact of radiation reaction effects on collective plasma dynamics. This interplay between QED processes and plasma physics, or this extreme radiation process in plasma physics, has many implications in different areas, both in ultra intense laser and particle beams, and in relativistic astrophysics. What I'm going to tell you a little bit about is more on the fundamentals, and then I'll try to motivate this a little bit with some possible examples of exploring this in the laboratory. So this is kind of the most fundamental process that one needs to address when starting to think about the dynamics of charged particles in the presence of intense fields. Particles will radiate under this very strong acceleration. There are many ways, or there have been many ways to describe the classical process. Now there is let's say a consensus on what should be the approach, and we have what I'm going to show you is results that are based on numerical solutions of both the Landau and Lifshitz radiation reaction equation and the QED radiation reaction equation. So my plan is to show you how radiation reaction leaves an imprint on the distribution function of a system of charged particles, and how this then leads to the onset of electron scale kinetic instabilities. The consequence of these kinetic instabilities is the generation of coherent radiation, and we think this is relevant in astrophysics, but it can also be probed in laboratory scenarios. I'm going to show simulations. They have been done with Osiris, but of course, many of these results, they are so simple setups that I'm almost sure that anyone that has a peak code can test these ideas and check check some of these ideas. To test this, of course, you need a particle in cell code, and as in any QED peak codes, you need a way to extract energy from the charged particles that are radiating. And so I will show results where the force, the back reaction on the particles is either quantum, like it's described here, or it's classical with the Landau-Lifshitz formula. To motivate this, I would just like to highlight a particular point of radiation reaction, that it's very clear when we look at the expression in the most simple setup. So if we assume a very strong magnetic field and we look at the expression of the radiation reaction, we see that there is a dependence that is very clear here. That essentially states that particles with higher perpendicular momentum will radiate faster. Okay, so if we we call this a differential cooling. So particles with higher momentum, perpendicular momentum, are cooling faster than particles with lower momentum. And so if we just look at the single particle dynamics, a very simple setup, you see that these particles, they started with the same distance in momentum, but as they cool down, their distance is shortened. Okay, so you can imagine that if you have a very large ensemble of particles, this will have a consequence on the charged particle dynamics. This is what we've been exploring. So if we look at the reduced distribution function, so you have an ensemble of particles that have some thermal spread, some perpendicular thermal spread, and now you let this evolve, and what you'll see is that the distribution function will evolve and develop these features. This can be explored in detail, and from a theoretical and analytical perspective. And we, of course, need to start from the Vlasov equation, where we add the extra radiation reaction force. And if you assume this particular setup where we have a constant B field, then I'll describe other setups with other types of fields. We'll see that our Vlasov equation takes this form. Also, if you neglect the Lorentz force for using arguments of cylindrical symmetry. So now, if we plug in the radiation reaction force that I've shown you before, it's possible to combine both the Vlasov equation in cylindrical symmetry and the radiation reaction force for a constant B field, and get an equation that looks a little bit complicated, but it's possible to solve this equation analytically. There are a number of simplifications that one needs to do to be able to solve this equation by the method of characteristics, but it's possible to solve this equation analytically and get the full solution for the evolution of the distribution function as a function of the initial conditions, in particular the initial distribution function. What is interesting is that the same formal structure has been also shown to be relevant when studying runaway electrons in fusion plasmas, and similar findings have been also recently published in the Astrophysical Journal. So much of this work has been published recently in physical review letters. So this is very exciting. We have an analytical expression for the evolution of our distribution function, so we can now model any plasma undergoing in these conditions. And what is interesting is, independently of the initial distribution functions, it's possible to demonstrate that whatever are the initial conditions, you always develop within a finite time a ring-like region. We call it a ring-like region, and I'll show you why. Rings where the derivative of the distribution function with respect to the perpendicular momentum is larger than zero. So let me show you a few examples of the analytical solution for this problem. So we start Gaussian Hüttner power law, and what we see here is that as the distribution function, as the electrons cool down, you see there is a region that is marked here in red that develops regions where the gradient of the distribution function with respect to the perpendicular component is larger than 0. These are inverted Landau populations, and we know from any classical textbook in plasma physics that these distribution functions are going to be unstable. So this is quite exciting, because this tells you that a plasma which is subject to a plasma that is subject to very strong cooling, we need to take into account that the distribution function will evolve in a non-trivial way, and it will develop these inverted Landau populations. Of course, there are timescales that one needs to compare. So the cooling cannot be too slow, but as compared with other timescales of relevant for the plasma. But what is relevant here is that there is a universal behavior that we expect from a collisionless plasma when we include radiation reaction. We can, from our analytical model, it's possible, for instance, to predict how the distribution function it will evolve, and if we go back here, if we have this the formation of these structures in the perpendicular momentum of the distribution function, you very easily realize that what we are creating here is a peak of the density of axis with respect to the perpendicular momentum. So we are creating rings in the distribution function. So from our analytical results, it's possible to describe and to predict how this ring evolves. And this is a simulation where we have a very hot plasma undergoing synchrotron cooling, and we are predicting the radius of this ring. And this is a comparison between the theory, which is plotted here from these results, and numerical simulations that have been performed either with classical radiation reaction, with QED radiation reaction. In this case, we don't expect significant differences, because the chi, we call it the chi thermal, is 10 to the minus 3, so things are quite classical, let's put it this way. So it's very clear that we start, let me play the movie again. We start with a hot plasma, Maxwellian plasma, and very quickly it develops a ring. Okay, and this is the predictions from the theory that really match the simulations. Let me just make this a little bit more visual. So again, this is a movie showing the momentum distribution function along the 3 different directions. We start again with the Maxwellian. So this is not obvious from the initial condition, but the color scale is chosen such that the late time evolution is clear. And so as we start, we have all the plasma particles rotating as expected, and we have the strong cooling. We already have some cyclotron emission, so we have radiation, which is occurring on a range that the simulation grid does not capture. As from synchrotron, but we also see some radiation at a much lower frequencies, and this is captured by the grid. So now we have these rings. So what are the consequences of these rings? So as I've told you, we know from plasma physics textbooks, whenever we have these positive gradients in the distribution function, these will be unstable. And so let's see what happens. We just let the movie continue, and we'll see that the ring will start to go unstable. And this instability, which is called the electron cyclotron maser instability, leads to bunching in the azimuthal direction. The main consequence of this is, as expected, you have a ring which is being modulated in the azimuthal direction. You start to have radiation, and this radiation can be coherent. which is quite exciting. And for the parameters, when we translate these parameters to astrophysical conditions, this is emission in the radio waves. So we have a clear impact of a radiation reaction on the collective plasma dynamics, and then this leads then to a clear signature in another region of the spectrum that we can aim to probe, and it is can be associated with several of these compact objects. So the electron cyclotron maser instability has been considered a source of coherent radiation. There are many. This has been proposed by Donald Melrose many years ago, more than 50 years ago. He has proposed this to explain coherent radio emission from pulsars. But one of the open questions was always, how do we get plasma conditions such that the instability can be triggered? And so it seems that we have here a possible channel that naturally leads to the conditions where the electron cyclotron maser instability can be triggered. And this is another simulation that illustrates what we should expect when we have a finite plasma. So now I'm showing a two-dimensional simulation where we have some gradient here to make things on the density, to make things a little bit clearer. And if you look at the distribution function across the transverse dimension, we see first bursts of radiation as the ring is formed. Then the ring is formed, it goes unstable, and as it goes unstable, it starts to radiate coherent radiation. So these findings came in parallel with the findings of another group, not for the electron cyclotron maser instability, but for the fire hose instability. So I just also would like to point out to their paper that addresses similar results. There are no comparisons there with the numerical simulations, but in essence, the similar predictions for a different range of parameters are also present in that particular paper. What happens? I've shown you results for very relatively low magnetic fields, so that we need to run this for a very, very long time. So the equivalent chi is 10 to the minus 3, 10 to the minus 4. And what happens when we ramp up the magnetic field and what we call the chi thermal starts to be close to 1 or over 1. So of course, with numerical simulations, we can run with the classical radiation reaction pusher and the QED pusher. This is what I'm going to show you. And you can more or less guess what's going to happen. So the ring on the classical description is going to be much well-defined and very clear. On the QED description, you still get the ring, but of course, there is the inherent quantum stochasticity of the process leads to some ring width that we can predict. But still, what is important here is that even for these conditions, we get these gradients on the distribution function that will lead to the instability. These conditions in particular are relevant when we are talking about highly magnetized neutron stars as magnetars. And so this is also a very interesting regime. So the point here is that for exactly the same conditions, after the strong cooling, the beam radius in the classical description is significantly narrower than on a QED description, but we still get the same type of structure. What is interesting is that the interplay between the radiation reaction and instability brings novel dynamics. Depending on the range of parameters, we can have bursty behavior. And I'm going to show you this. So in this case, we already gone through the cooling phase of the ring. So we have just a ring which is very well formed, and now we let the instability start, and we look at this process with the radiation reaction on or off. And what you see in two cases is that in the case where you have an open system with radiation reaction on, you have significantly more emission, and you have also a burst emission. This is an important point when describing these systems, because one of the saturation mechanisms for the instability is the amplitude of the generated coherent radiation. So this will lead to the diffusion of the ring. So if our system is open and the generated radiation can leak out of the system, then the radiation reaction, if the temperature of our system is large enough, can kick in again and lead to a stronger contraction of the beam again, and then we get a cycle here, or a few bursts of emission of the radiation. So there's very exciting dynamics on these processes, and we have worked out the theory to look at saturation and what are the expected emitted powers, and this is going to be published soon. This is based on quasi-linear theory, but then compared with the numerical simulations. So I think this is a very, even though this is a relatively simple scenario, this is very, very interesting, because it's a very clear example of how these strong field processes have a direct impact on the plasma dynamics, which is something that in the laboratory is quite hard to achieve. So if we really want to understand how far are we from probing QED with plasma, these interplay between QED and plasma physics in the laboratory, we are talking about having to go into conditions where the density, for instance, the density of electrons and positrons needs to be quite high, and different authors have explored the different conditions, but it's quite challenging to see the feedback of QED processes on the collective plasma dynamics and the modification of the plasma, the properties of the plasma, as clearly as we are seeing in this particular case. So if we could devise a setup where this could be explored and probed, I think this would be very exciting. From previous studies that we have done with beams, we think that probably there is one of the settings where some of these ideas can be explored. So I'll just want to share with you one of the ideas that we are exploring is to look at radiation cooling resorting to laser wake field accelerated beams. So we know as a laser propagates through a plasma, it generates this wake. Particles are injected on the back of the bubble. They undergo betatron radiation. So if we play with the parameters of this beam and the parameters of propagation of this beam in the channel, we can explore how betatron cooling happens in these channels. And it's quite interesting, because the structure, if you look at if we look at the chi that some of the electrons on a beam propagating inside the betatron channel, this can reach values close to 1. So it means that we are in conditions where this strong cooling can be important. This is an example. This is not an optimized example, so we are working on this at the moment, where we just have a beam with a gamma. So it's a 1 GeV beam, so it's not even a very energetic beam, with some divergence propagating in a background plasma. The density is a Mach density. This is not yet realistic, but we take advantage of the fact that the betatron, the force associated with betatron cooling also displays differential cooling, and so we can take advantage of this and explore similar physics. And this is what we are illustrating here on the evolution of the perpendicular momentum of the beam. It also develops this ring-like structure that we can then probe and use for applications. So I think this shows that we have here a very exciting research direction, in our opinion, where something as fundamental as radiation reaction in a constant B field actually has an impact on plasma dynamics. So my summary to conclude, I just like to convey to you that there are even some surprises on when we start to look at the fundamentals and at the fundamental kinetics of plasmas undergoing strong radiation emission processes. The intrinsic nonlinearity of radiation reaction can trigger kinetic plasma instabilities, and these instabilities can be sources of coherent radiation. We have developed a theory for this and simulations that confirm the relevance for this process. And when we plug in the numbers, there are a number of astrophysical scenarios where this can be explored. And we think there are also, we can devise, at least in this first step with betatron cooling, or other experimental conditions where these can be explored experimentally. Again, thank you very much, and I would like to acknowledge again my Pablo Bilbao that has done all the hard work. And so, if you want to know more, look up the recent paper, and we have upcoming papers very soon that will where we'll share some of these results. So thank you very much.
So thank you, Luis, for this excellent talk. Very exciting, as you say. It's like a really nice application. Result. So questions. Matteo.
Okay, thank you very much, Luis. Very nice talk. It was exciting physics. I wanted to ask you, what happens if you have some spread, longitudinal spread in momentum?
So what I've shown you, the simulations that I've shown you, they all start with Maxwellians. Okay, so there's as much spread. Okay, let me. I think this movie here is probably the best one to illustrate this. Okay, so this is a Maxwellian with a large thermal momentum spread. So in all directions. So we can see that of course there is transverse cooling, but there is also longitudinal cooling. Right. So this is somehow a little bit more well known. We know that as particles undergo radiation reaction in the longitudinal direction, there is also a compression on the distribution of parallel momentum. The paper of Maria Vranic in Physical Review Letters addresses this very nice. So if you start with a Maxwellian along the longitudinal direction, you turn on radiation reaction, you have a slowdown of the beam, and you have a compression of the beam. Right? So the longitudinal dynamics is not surprising. What is surprising here is that transverse dynamics, where this asymmetrical compression, due to the fact that it's in 2D, leads to the formation of these gradients in the perpendicular momentum. Yes. So on these simulations, everything is accounted for. We can also look at these simulations as simulations done in the beam frame, in the beam rest frame. But they have thermal spread in the longitudinal direction, in the transverse direction, and for these particular cases, they are the same. So we start from Maxwellian distribution functions.
Okay, and if I may very quickly, if there is an electric field like disturbing the system, is still robust, and up to which point?
Yeah, that's a good question. Depends on the orientation of the electric field. So if it's so what we are doing right now is revisiting most of the plasma, the drifts, particle drifts with the radiation reaction, and so if it's so a E cross B drift is not modified. So if your electric field is, depends on the orientation of the electric field. So I cannot give you a universal answer, but it depends on the electric field. Yes, but for some cases it will not have a big difference. It will not have a big difference.
Okay, thank you very much.
So there are two more questions, Evgeny. Not too long.
Okay, thank you very much. Very interesting. I wanted to ask you about these rings in a quantum and classical regime. I think it maybe was a next slide.
Yes, yes.
Yeah, this one. So actually, as I understand, you can predict like analytically, for example, the radius for the classical, right? Is
Yes.
it possible to determine, for example, the thickness of the ring in the quantum regime somehow, like depending on
we don't have it's not as a beautiful analytical result as when you solve and when you have an analytical solution for the Vlasov equation, but we can estimate this. There are estimates. I'm not sure if they are in the paper, but we have those estimates on the width of the ring that will depend on the chi thermal and what we call the chi thermal and all that. Yes, that's possible.
Thank you. And Zain?
A quick question. Thanks for a very nice talk. My question is, which kind of parameters influence the radius of your ring in momental space?
Yes, I'm not sure if I have the full expression here. Yeah, I'm sorry. I don't have an expression here.
You can briefly mention a little bit.
Yeah, but this is essentially determined by the what we call the chi thermal, and which is a chi parameter that is weighted by the distribution function. Okay.
Oh, okay. Thank you.
Okay. But one important thing, let me just point out, if when you look at the structure of the Vlasov equation, and if for any radiation reaction, for any range of parameters, you will always develop these gradient in the distribution function. What is important is how fast the process is occurring, okay? Yeah. And this is determined by what we call the chi thermal parameter. So the higher the chi thermal, because then of course you need to compare this with other typical processes that might occur in the plasma, okay? Collisions, diffusion, and all that of the system. Okay.
Thank you. I will check out your paper.
Yes. Thank you.
Thank you. So that was a nice discussion. If there are no further questions, that I don't see. So we thank again Luis for this really extremely interesting talk. And,
okay, thank you.
And the next speaker is Matteo Tamburini.
Yes. Okay. Okay, can you see my screen? Do you see?
Not in the good format. We see the next slide as well. So maybe you can copy.
Why I get distracted? So I have two screens, and one is showing the full of it, and the other no.
Yeah.
Let's see if I think maybe I have to remove one of the screens, but I have to disconnect for this.
I think it's okay. I mean, now we see only one, right?
Yeah, but it's not full screen, right?
Yeah, but I can just make it bigger on my screen. So just
okay. Then I go on with this. So with
I don't know how bad it's for the others, but I think if you switch off,
can you see everything?
For me, it's okay.
It's good.
Yeah. Okay.
I mean, there are some features that disappear if I don't go full screen. So, wait a minute. Disconnect.
Okay, so do that.
Hello?
We hear you now.
Yeah, we can hear you. So you're back with us. So you want to try to put full screen?
Okay, I'm back. So fine. Sorry for this. I basically had to disconnect.
So you want to try full screen again?
Yes. Now?
It's the same. Oh, no, it's better. Yeah. Okay.
Great. Perfect.
Okay. Thank
So
you very much. If you can tell me maybe when my time is close to finish, that would be helpful. Okay. So can you hear me?
Yes, you can go.
So the title of my talk is Interparticle Fields Amplify the Radiation Reaction. And first of all, I would like to thank the organizers for inviting me and for the opportunity to talk today. What I will be discussing today is something that has been obtained very recently. And in fact, the preprint appeared this week. And that's been done in collaboration with my student, Michael Quinn, who took care of writing code. And there are some noise in the background. Okay, thank you. With my student Michael Quinn, we developed the code around the simulation, and with Antonio Di Piatti and Christoph Keitel at the Max Planck Institute for Nuclear Physics. Okay, let's start a little bit with an introduction to review what is radiation reaction. So radiation reaction is a very old problem. It has been studied a lot. And in classical electrodynamics, the key problem is that the field diverges on the word line, right? So basically what you have to do in classical electrodynamics is to give a particle some kind of size. You make it a sphere or a shell or something like that. And at the end, after you have made the calculation, you take the point limit. Now, this is well known to lead to problems. It leads to the Lorentz-Abram-Dirac equation, which is present also unphysical solutions, so runaway solution and so on. But nowadays, we are more or less convinced, or broadly convinced, that the so-called Landau-Lifshitz equation, which is obtained from the Lorentz-Abram-Dirac equation by perturbation, and whose main term is reported here, which is kind of frictionalized force, we have seen also with the previous talk by Luis, is kind of correct. So, I mean, from all the practical point of view, when we are in the classical regime, namely the chi parameter, which is the field experienced by the particle in its rest frame, is much smaller than unity, this equation is basically correct, and is mostly, the effect is mostly comes from this kind of friction-like term. So now what happens when we have a system of particles? This is the question. Now we have a system of many point-like charged particles, how to deal with that? And there were some studies, and one of the possible answers is, okay, we expect that it emits coherently. If these particles could move together, then we could note that if we kind of rescale, so the particles move together, we rescale the n particles with the charge and the mass, we get basically an electron radius which is modified, right? So if all particles could move together, we would have an effective electron radius which is larger, and so this force would be larger, and this was been termed coherent amplified radiation reaction. Now the problem is that this is a bit too simple, and the situation does not work too well. We'll discuss why in a moment. So we have a system of n-part like charged particles. Can we deal it with a single superparticle? Then the particles must move nearly in the same way. Is this realistic, and do particles influence one another? Now, it is realistic, we will see later, but of course there are many situations where this certainly does not work. And the first thing that you could think is a very simple example, that if you have n equally spaced particles moving in a circle, and then you put many of them, so many particles, they form at the end a steady current, and this steady current emits no radiation. So this is a stark disagreement with the sum of energy lost by each particle. So if each particle is treated independently, I predict a lot of energy loss, while if I keep into account everything, basically there is no loss at all. And certainly this cannot be described with the superparticle model situation. It's very clear because they don't move in the same way. So the key message is that to be very rigorous from the, strictly speaking, the fields must be superposed before evaluating the equation of motion. You cannot just forget the fact that first you have to superimpose all the fields and then evaluate the equation of motion. And so what we are going to do is to consider a coherently radiating electron-positron bunch, okay? And the electron-positron bunch, because the initial idea was that we don't want to have some global field. We would globally want the system to be neutral, current and charge and current are neutral. So before going to the simulation results, let's talk a little bit what is the numerical scheme. What are the typical approaches for solving the Landau-Lifshitz equation? And this involves the fact that analytically particles are treated independently. This is absolutely standard thing. So each particle is evolved in the external field, either have the trajectory, either have the dynamics, and draw the conclusions. The problem is that this is actually inconsistent with many particles, or when a lot of energy is emitted coherently. This is very inconsistent. And from the numerical point of view, how do we deal with this kind of problems? Normally, we include the external field, of course, and we include the mean field from the charge distribution. Also, with particle and cell codes, we have always to remember that we have macro particles that actually the full approach is designed to simulate this continuous distribution, this kinetic distribution in the phase space. And so here the problem is that you neglect the fact that you have point-like particles. So the point-like nature of electrons and positrons with these fundamental charges. Now our approach is quite fundamental. So we really go to the first principle. So we want to solve the Landau-Lifshitz equation with the total field for point particles. So basically the total field, and this will be for each particle, is just the sum, so linear superposition of the external field, which could be a laser or any other external field, and the interparticle field. So what is the interparticle field? So it's really the particle generated from the linear Vickers potential, so the fundamental thing. And we have to consider that each particle then will experiment the external field and the field of all other particles. But on top of this, there is a difficulty which we have really to keep into account retardation effects. So for each particle, we have a retarded time. We have basically to register the full trajectory, the full history of the particle. And at each time step, so this is a kind of n-body problem, we have to consider all the possible interaction plus the retardation effects. But so resolution of the problem from first principle, from the point of view of classical electrodynamics. And then we have basically this kind of equation, right? So we have the Lorentz force and all the other fields in the Landau-Lifshitz, but here we have the contribution of the external field and all the field generated by all the other particles. Now, in designing what kind of system we could study, what it could be interesting, let's try to identify the parameters from the single particle spectrum. So if we had a single particle, single electron, suppose, what would we expect? We would expect, like for circular polarization, a spectrum that starts from this frequency, which depends, of course, on the gamma naught of the particle, the frequency of the laser, and the A naught. So it starts from this wavelength, so this frequency here at the bottom, and goes more or less up to the Doppler shifted one for 4 gamma squared of the laser frequency. If we had linear polarization, we have a broader spectrum. We go up to, say, 4 gamma naught squared. So it's A naught is further broadening the spectrum. Okay, so they're not much larger than one, the spectrum is really broad. Now, how should we imagine this bunch to study these kind of effects, this coherence effect? So the idea, naively, I would say, okay, if we make the bunch, the size of this electron-positron bunch small enough, so say smaller than this wavelength corresponding to this frequency divided by 2, and we send it, you let it collide with the laser, then we should see, at least we expect, one would expect, oh, this part of the spectrum probably is coherent, and we see some transition to the incoherent part, and we see how this changes the dynamics. And how should we choose A naught and gamma? Okay, we should choose A naught comparable to gamma, because what we want to of course, is we want to have the bunch cannot be arbitrarily small, of course, and we want to many of these wavelengths to be coherent, and we want to avoid the backscattering, so we cannot really push too much that the bunch comes backward. And with this kind of intuitive idea in mind, we come with some possible choice of laser and parameters. So to make the thing simple, we basically approximate the laser as a plane wave pulse, but I want to already tell you that we tried also with focus pulse and it works equally well. So to make things simple, we start with the plane wave pulse, we describe like this. The plane wave pulse is counter-propagating, of course, with the bunch. The bunch is supposed to go along positive z direction, so the plane wave comes in along negative direction. We consider two kinds of polarization, so linear and circular. They are made in such a way that the laser has exactly the same energy. So this plane wave has the same energy independent of the polarization. And we consider two sets of, so a scenario which involves two lasers. Actually, the bunch is collided with just one laser, but we have two situations, and it will be clear later why we consider two situations. The first situation is that the bunch collides with laser 1, so to speak, where the wavelength is 400 nanometers, the intensity is 10 to 20, and the then is 5. And the duration is like 30, a bit less than 30 frames per second. And what we expect when we collide this with our bunch, which has not a large gamma factor we have chosen to be 5, so the same as this A0. And we get the chi of 10 to the minus 4. So we are clearly in the classical regime. Another situation is where we basically, what we change is just the wavelength of the laser and correspondingly the intensity. All other parameters are kept constant. So we go from 400 nanometers to 100 nanometers. And then since we want to keep A0 the same, of course, we raise the intensity to 10 to 21. So, and chi remains always well below below unity. So before going to the simulation, let's have a look a little bit what we expect for the transverse dynamics at the peak of the laser, okay? We have now 4 cases, so the 400 nanometer wavelength, 100 nanometer, and for each of them, circularly polarized, linearly polarized, circularly polarized, linearly polarized. So what do we expect? So we expect that when the bunch collides with this laser, and if for instance, is 400 nanometer, then of course the electric field, the transverse electric field of the polarization will transversely deflect, okay? The electrons are positive because the opposite charge will go into opposite direction. Now, for the 400 nanometer circularly polarized, the wavelength is large enough that the bunch basically, so the electrons are positive, almost basically completely separate, almost completely. And they start to rotate following with the rotation of the electric field. So they kind of perform this circular motion. Whereas if we go to linearly polarized, what we see is that they separate and then they recollide, separate, recollide, separate, recollide, and so on. The difference is that when we go to 100 nanometer, now the bunch, the wavelength is shorter. So what we see is that the bunch actually, they stay on top of each other. So they still rotate, but they are kind of one on top of each other. And still with LP, they will recollide, but they don't really separate. They remain one on top of each other. And just to specify from the very beginning, the bunch parameters are chosen in such a way that basically the particle density is 4 orders of magnitude smaller than the critical. And the critical density, which means that basically this bunch is transparent or almost completely transparent to what you send to the laser. And the plasma skin depth is more than 1 order of magnitude larger than the bunch size in its average rest frame, which means that basically kind of streaming instability cannot really develop because it's really too small. The bunch consists of just a few thousand of particles. They are really too small, and this not sufficiently extended to trigger some kind of streaming plasma instability or something like that. So what do we see then if we run the simulation? So what we see, of course, that the bunch after some time, surprisingly, gets modulated, and the way it gets modulated, it depends on the wavelength, depends on the polarization. If we look to the longitudinal direction, so the longitudinal distribution of particles for the CP400, we see that basically if we have only the laser field, so we just consider the external field, the shape of the distribution is preserved. It remains the same. But if we include also the interaction of particles, we see it gets skewed. It gets some shifted towards low energies. Instead, if we look to the 3D distribution, for instance, here, we see basically there is some kind of expansion with no clear structure formed. Instead, if you go with LP, what we see is basically that there is a sharp peak formed. So again, if we neglect the fields generated by the particles, the shape is preserved. But if we consider the field generated by the particles, see that basically we have this sharp peak. And if we look to the 3D distribution, we see that really particles kind of bunching towards the rear of the propagation direction. If instead we do the same, but with 100, we see basically some much more complicated structure. We see that basically the formation of 3 peaks here and also here. Here is both for CP and LP. So kind of the difference is not so strong anymore. We see 3 peaks. And we see that basically these peaks kind of have a distance which is comparable to the wavelength, to the lower wavelength that you could emit. So this lambda has to be very clear corresponds to this quantity here, lambda here, which corresponds to this wavelength here. So we see that we get these modulations, and we see that the difference between circular and linear kind of becomes much less, or it's much less pronounced when we go to the 100 nanometer. Okay, this is for the distribution. Quite interesting. Let's have a look to what happens. So we have seen kind of micro bunches, so modulation of the bunch. Let's have a look to what happens if we look to the spectrum. So now we look to the spectrum. We consider a detector, which is 1 centimeter square from the point of surface and 1 meter from the point of collision. From the point of bunch, there's a collision. And we consider 3 cases. So laser only, which means we consider only the external field. Laser interparticle, which is where microbunching is seen, we discussed, we showed you before, which means that basically we include everything. So the external field and all interparticle fields, and another intermediate case, we call it laser interspecies. Basically, it's the same as laser interparticle fields, but the species do not see each other. So electrons do not see the field generated by positrons. Positrons do not see the field generated by the electrons. It's kind of as if we kind of remove one of the 2 bunches. And let's see what happens. So these are the spectra. So the first row here shows the results that we see if we do the correct thing. So we kind of make the coherent superposition. We really look to the spectrum, the complete spectrum. The second row shows the same results that would be obtained if we sum the contribution incoherently, like the same trajectories, but each particle gives its own contribution separately. Why we did this? Of course, because we want to identify the regions, very clear, the regions where emission is coherent by comparing the first and the second row. And again, here, if you look to the to this figure, you will see there are 3 cases. The laser only case here, which is in orange, laser interspecies is light blue, and laser interparticle species is dark blue. So what is striking, if you immediately look to this, is that there is a big difference from the CP400 and all the other cases. Okay.
Matteo, you have 3 minutes.
Oh, really? Okay, then I speed up. Okay, thank you very much for telling me. I will have to speed up a little bit. So what happens is basically that the region which is coherent with laser only, it corresponds basically to the frequency, which is the original site of the bunch. Now, if instead we consider interparticle fields, then we see that this region extends much more and extends to much higher frequencies. And this 280 electron volts that I show here corresponds more or less to the side of this microstructure that formed there. So the origin of this coherent emission, which extends to very high energies, to 300 electron volts, roughly speaking, is because of the formation of this microbunching due to the interaction of particles with the field generated by all the other particles. Now, the same thing is seen if we look to the energy. What I want to say here is just basically that, of course, what we see is, again, that without only the external field, we see basically the distribution is perceived. Actually, we see contraction of the phase space a little bit. Instead, if we consider all the interparticle field, we see that there is kind of a kind of expansion. So I would say that collision plasma kinetic equation with the mean fields and classical radiation reaction predicts phase space contraction. It was studied a long time ago, shown a long time ago. And this kind of showed that we are already beyond the mean field approach. So really we have to consider that we have a system of point-like particles interacting with one another. Just very briefly, what I want to say is that this amplified emission also feeds into the radiation reaction force. In fact, with the radiation reaction force, we see that the losses are larger. So you really change the dynamics. You really change how much energy you send into the radiation reaction, into this radiation. I want to show a simplified model of the energy transfer. But I think I'm running out of time. So basically, I would just want to give you an intuitive idea. So depending on the position of the particle inside the wave, so you can imagine that you have a particle and co-propagating radiation. So depending on the position of the particle inside this wave, you may have two situations. One is that you gain energy from that, or you put energy like that. But on average, this tends to average to zero. Now, only in specific conditions, namely there could be a sustained energy transfer, that particles transfer energy to the radiation field. And if you develop a simple model following similar ideas as that of free electron laser, what you find is that this model predicts that the wavelength where this occurs, so this sustained energy transfer occurs, basically corresponds to this wavelength that I said before, so the lower coherent energy emitted by a single particle, at least when the NOT is much larger than 1. Now I come to the conclusions. So what I want to say is that the experiment observing radiation reaction involved the collision of GeV electron beams with ultra-intense laser. This has been seen, for instance, with these two experiments published in 2008. Here, what we have done is we have identified a new regime where we leverage the interparticle fields to show that radiation reaction becomes significant at MeV energy with barely a few thousand particles. So this is really a system of few particles. And all the effect is determined by the discrete nature of point light charges, and that really changes the dynamics and leads to the huge amplification of radiation reaction emitted really to a very broad range of frequencies. And this also increases the radiation reaction itself, because the fields are so strong that really feed into the radiation reaction force. And the effect actually is, and this is a quite sub point, is that you really need two species, because if you look to what happens, if you have just a single species, you don't see anything that strong. And it's really the radiation emitted by one species that feeds the emission and the radiation reaction of the other species. So thank you very much for your attention.
So thank you for this extremely interesting talk. So there is already one question, Yoshide, and sorry if I mispronounce, but please go ahead.
Okay, thank you so much. The talk was quite clear for me. Thank you so much. I have one question: how you can determine the scale of the bunch size of electron and positrons? Which physics behind the scale of the bunch size?
So the scale of the bunch size, so
10 nanosecond, 10 nanometer, something like this. I don't know the exact number.
So as I mentioned here, the initial idea was we want to have, the naive idea was we start with something where we want to have this bunch size smaller than this. So because the idea was we will see probably some coherence here, and then we see transition to incoherence. Now, what it was interesting to observe is that this idea, which was motivated by physical intuition, actually is not quite true, because actually you observe these kind of effects even when this condition is not fulfilled, namely when the bunch size is actually larger than this. So this thing is shifted toward higher energies. And this is specifically the example. I had no time to discuss too much in the details, but here, right? So if you look, so there is a difference in the longitudinal scale of energy from the 400 and the 100. So for the 100, basically, if you look, in fact, to the orange curve, you will see that basically there is never any coherence, okay? But still, the fact that there is this emission can still modulate the bunch, even when the bunch is actually larger than that. So there is no necessarily a size which fits all. Of course, we didn't want to make the bunch large, also because we don't want to have, in this case, kind of other plasma effects like instabilities to trigger in. And of course, also because it's hard to simulate this, but I just want to say that...
Okay, understand one point. If we want to declare that this is a coherent, we need a narrow, small size, like a 10 nanometer, something like this. And you want to compare between the scale of the band size and wavelengths for the external field. And if we use a longer wavelengths for the interaction for laser part and the shorter wavelengths, it's quite a different nature was happened. Like you shown here, and probably that could be, I catch by your statement.
Okay.
Okay.
Thank you.
Thank you.
Sounds good. So Evgeny and then Luis. Evgeny?
Yeah, hi, Mateo, thank you very much. Very interesting talk. I wanted to ask you a bit more about this electron-positron thing. So do you say that if you would have only one species, only electrons, you wouldn't have this enhancement, let's say, of the radiation due to coherency? Or I got you wrongly?
It's much less. It's much less, and sometimes there isn't. Sometimes it's much less. So these figures just show you. Now, your case would correspond to laser interspecies. So this light blue here, because in this case, basically, electrons do not see positrons, and positrons do not see electrons. Okay. Mm-hmm. Now, the point is that first you have Coulomb, which wants to make the bunch explode. First thing, and in fact, this kind of you see, it's perhaps not so easy to see, but you see it's a bit lower here than the orange one. So if you had only the external field, and there is some amplification here at higher frequency and also here, but much less than you would see with the electrons and positrons, and actually most often much less than you would see only considering the external fields, because the external field, this is a log-log scale. So something that looks small here is not so small. So we are varying by orders of magnitude. And you see the light blue perhaps is not super clear, but tends to really to stay all the time below the orange one, which is, you consider only the laser fields. And
sorry, sorry for interruption. Just quick question. So, but what you're telling about is relevant for linear polarization. For circular polarization, the difference is not that high, at least for low frequencies, right?
And yeah, but this is just because of the fact that basically for these 400 nanometers, the bunches, we are in this situation here, the bunches do not see each other. They move in this circle and don't see each other. In fact, if I go to this situation where the bunches see each other, they are on top of each other, they still do the same dynamic, but on top of each other. And then I get the 100, and the 100 is circular and linear. And then, I mean, we still see something. So, for instance, in this case, with you would see that it's more than just considering the external field, but still many orders of magnitude less, and doesn't extend so much as when you consider electrons and positrons. So there is also something there, but it's much less than you would have. It's much weaker. The point is that this bunch tends to expand. The particles don't want to stay very close to each other. So
it's interesting because it doesn't correspond to what I see in peak simulations. I also made like with just electrons and electron positrons, and I would say that, but for circular polarization, I don't know about linear, and I don't see much difference if I have, let's say, the same density of the bunches.
Okay, so
but yeah, it's interesting to.
Okay. No, I want to say that depends, as I said, how they are. So on the parameters, if the bunch overlap or do not overlap. The problem with peak simulation, we actually did something like this. But the problem is that with peak simulation is that you have these macroparticles. You cannot, if you try to make look like very, very dense, very, very localized, you start to have a lot of actually numerical problems. So you have really troubles when these particles are, if you really want to see point-like particles, the field of point-like particles. And in this situation that we are here, as I said, peak probably is not the right tool precisely because we have very few particles. So it's not that we don't really have a plasma in the proper sense. It's not sufficiently extended, it's not sufficiently dense at the end of the day.
Okay,
no, Evgeny.
Yeah, sorry.
I think it's a super interesting discussion and food for thoughts, but I think you can exchange later, and it's a very important point to consider. So please, Luis.
Yeah, thank you for the very nice presentation. Your presentation kind of reminded me about these optical undulators. Where you collide electron beams with lasers, and there is this regime which is called inverse Compton scattering regime for undulators that I think has similarities with what what you are exploring here. So I think it's worth checking what they have done there, because I think they also include they might also be thinking about radiation reaction and all that. I had kind of two small questions. So when you talk about external fields, is this the beam field that you're adding up there, or because you have laser and external fields? This is one part. The other part is that somehow regarding your critique of peak simulations, the way to do these simulations, you do these simulations in the beam frame. So you boost, your beam is stationary, and you boost your radiation field to the rest frame of the beam, and then most of course you need to run with very high resolution, but this avoids some of the numerical problems that you were mentioning.
Okay, so I will try to respond very briefly. So indeed, you're right about the free electron lasers. There are similarities, and the model, which I kind of I had no time to explain, sorry. It's kind of borrowed from the idea that are used in free electron lasers, although this is a different regime, really completely different. But it's true that this kind of interaction between radiation and particle is similar to that of free electron lasers. And then I will move to the other question. So no, the external field here is the laser field. Okay, the external field is the laser field. All the rest comes from all the other particles. So it's an body problem. So each particle, it's
the self field of the beam that that you're accounting for here, right?
Yes, I mean the field generated by each particle. So at the end, the field of the beam will come because of each particle is interacting with each other. So it is creating this.
Mm-hmm. I think this is also connected to the question in the chat. If you have a look, that is actually asking some detail about the.
Yes, I use this code is anybody. So we go for really point-like particles interacting with the linear Witcher fields from fundamental principle, basically. And the comment about the point of the peak, I mean, the peak is always, as I said, the problem that you can also go into the frame of and try to raise the resolution. The problem is that you want to put more or less the same charge, and the size of the cell you are making increasingly small. But the fact is extremely difficult if you want to do this in 3D, because you have really to resolve the interparticles. You have really to make it fine. The problem is that basically what happens if you keep the charge constant and make the size small, the density spikes. And we have tried this, and what we have seen is that it really leads to a lot of numerical effects, really a lot of numerical effects, like losses that are not there, even the single part. So a lot of problems, to be honest. And then we abandoned it, and we went to the first principle point and body simulation from first principle, including retardation and so on.
Nevertheless, I want just to kind of suggest you to look into these inverse Compton scattering FEL lasers, because there's lots of work there. So it might be worth comparing your results with the literature there.
Yes, thanks. This is actually a good suggestion. Thank you very much.
Okay, so thank you. And maybe, okay, I don't see other questions. I have a super short one before the next talk. So could you have a way of having a neutralizing background like ion-like instead of positron to check about the self fields, or it doesn't make sense?
I want to consider these kind of things. You could put the protons, but the protons, of course, they have very different masses. It kind of stays there compared to the electrons, and this also implies that so the electrons will be dragged back and forth, so outside and inside and so on, and the protons will neutralize for some time, and they don't really emit much radiation. So the fact that we have seen here that when the bunches get separated, they don't see each other, because, for instance, only for this 400 CP, they don't really see each other. They do this kind of motion. The radiation of one cannot see the other bunch, and then the effect is basically killed. I mean, we didn't try, but my feeling is that it's not going to work so well.
Okay. Let's conclude that, because we have a talk. So please, can you share the screen?
Can you see it?
Yeah, looks great. So the next talk is about electropolarization, ultra-relativistic plasma current filamentation instability. It's a gong. And again, sorry for mispronouncing, I'm sure, but go ahead.
Yeah, your pronunciation is very accurate. Okay. All right. Thanks for giving me this opportunity to show our recent work about electron polarization in ultra-relativistic plasma current filamentation instabilities. What is the plasma current filamentation instability? It can go back to the very more general Weibull instability. Weibull instability describes instability that initializes with an isotropic momental distribution configuration. It generates the electron perturbation and amplifies the magnetic field. The current filamentation instability is a specific Weibull instability that describes a scenario with the interpenetration of the counter-streaming plasma. For instance, if we consider the counter-streaming plasma along the y-axis, if we have a BZ field perturbation at the beginning, so this BZ field will deflect the electron current to generate the transverse inhomogeneity of the longitudinal current. So this way, the current density will further enhance this magnetic perturbation. So the positive feedback loop will be sustained, the B field and the current density. This is gave rise to this current filamentation instability. This is well studied by previous work. Actually, the current filamentation instability is a ubiquitous phenomenon in our plasma system. In the macroscopic world, the CFI can modify the electron beam energy deposition in the dense plasma. For instance, like in the fast ignition scenario in the ICF. So this electron propagates inside the dense plasma. This electron beam can be filamented. So another scenario is this CFI can also to influence the accelerating efficiency in the wake field accelerators. This is specific for the beam driven wake field. For instance, if you consider a beam, the beam could be filamented and eventually collapse in this propagation stages, so that the accelerated electron beam can no longer to get energy in this wake field. Very recent, the group from, I think from SLAC, they found that actually the ion transverse motion can also kind of enhance the Weibull instability after the normal saturation of the Weibull instability. This is termed as the kind of secondary Weibull instability. This is in fact another specific case of the current filamentation instability. For the astrophysical world, the current filamentation can shape the internal structure of the collisionless shock, because in the collisionless shock, in general, it can have a forward propagating plasma flow and also a background propagating plasma flow. So another interesting thing is this CFI can also trigger this stochastic electron acceleration in the magnetic reconnection scenario. For instance, this is an animation shown by Matsumoto's science paper. The electron do the multiple rebounds between each of this magnetic field. And during the magnetic reconnection, the electron can gain energy through this stochastic process. Also, since there are also many astrophysical ultra-relativistic jets explored by some black hole or massive neutron star engine, so this current filamentation instability can also modulate the afterglow coherent radiation follow this kind of jet explosion. So what our division interested is some strong field QED effect in the plasma current filamentation instability. Previously, our colleagues Benedetti and Matteo has investigated the current filamentation could give rise to a high efficiency gradient gamma ray sources. Besides, there is also another Russia group. They consider even dense plasma beam to interact, so they can produce the electron positron pair plasma in this scenario. Since here the emitted photon can interact with the further enhanced magnetic field in these filaments. So this nonlinear Brett-Wheeler process gave rise to this positron generation. So actually, both of these two investigation is based on the state-of-the-art techniques of the compressed energetic beam, such as the FACIT-2 facility. Our recent results show that the electron could be spin polarized in the laser magnetic field, so that we're wondering that whether this electron can also be spin polarized in the current filamentation instability, because in the current filamentation instability, we also have very strong magnetic field, and the electron has already shown that it emits high-energy gamma-ray photons. And whether or not could this electron spin polarization ratio are correlated with some detailed underlying filamentation instability mechanism. This is what we are interested in. Now we move on to our main topic, electron polarization in this filamentation instability. In fact, we found 3 different regimes with different electron spin polarization ratio features. Our interaction scenario is very simple. We consider an injected electron beam with energy around 1 GeV. The gamma factor is 10 to the 3 to 10 to the 4. We consider the underdense electron beam. In fact, this incident beam parameters, it just follows the upgraded FACIT-2 facility. They can provide us with a very dense and energetic beam. So for the background plasma, we just consider a kind of formal target or solid materials. In this case, our background plasma density could be 10 to the 22 to 10 to the 23 per cc. So in our interaction, we consider the dynamics in the transverse cross-section, which means that we run the 2D peak simulation. In fact, the 3D simulation is similar. We also perform the 3D simulation. The results show almost the same. The reason is that here the gamma factor is very, very large, so that the longitudinal perturbation is not very important to influence the electrodynamics. For instance, if the instant electron gamma factor is less than 100 or only maybe 10, in that case, the longitudinal effect, like the Kirk instability or the two-stream instability, will play an important role to influence its dynamics. We consider the periodical boundary condition in our 2D peak simulation. Also, to self-consistently consider the electron radiative spin polarization, we have implemented this model in the P-code epoch. So the key formula that to characterize the instantaneous electron spin quantization axis is this formula. From this formula, if you assume that the electron is not initially polarized, so this term coupled with the electron spin, and this term will get removed. So the only term that remains here is this term. This term, the unit vector of E2 indicates the local magnetic field direction in the electron instantaneous frame. So since here is a minus sign, this indicates that the radiative spin polarization effect will result in the electron tend to have a spin anti-parallel with the local magnetic field. This kind of theoretical work has been done by our theory group and Xianjiao University's colleagues. Let's take a look at the simulation results of 2 cases. Our incident beam electron with the energy of 10 GeV, with a density of 10 to the 20. If we consider 2 different background plasma electrons, one is 3 times 22, another is 10 to the 22. We can find 2 different filamentation regime. One is normal filament, another is abnormal filament. In the upper 2 panel, the brown color show the incident beam electron density. The blue and red color show the angle of the background plasma electrons. So in the normal filament case, this the incident beam electron is encompassed by the background plasma electron. in this scenario is kind of already being observed by some experimental results. So we term this as the normal filament. In the abnormal filament, the role of the beam electron and the background electron exchange. So in here, you can see that the background plasma electron is encompassed by the incident beam electron. So if you compare the local two panel, the local two panel show that the rainbow color show the electron spin polarization ratio. For the abnormal case, the spin polarization ratio is much higher. And the black arrow indicates the plasma magnetic field and its direction. Now, if we look at the normal filament case, the normal filament case, the electron start to be filament, and the small filaments tend to coalesce and get merged together to gradually grow up. This is kind of previously people has already identified this filament, so we term this as a normal filament regime. So the interesting thing is that the background plasma here, I show the red lines for the background electron motion. As you can see here, the red line just do multiple rebounds between each of the magnetic field. Here, the black stream show the magnetic field. You can see the background plasma electron do multiple rebounds between each of these filaments. That means the background plasma electron is not static. It's actually very dynamical. For the abnormal filament case, we found that, in fact, here, the key difference from the normal filament is, in this case, the background ion transverse motion is much faster than the incident beam electron. So the ion can be quickly transverse pushed, and the ion get assembled together. This ion assemble also attracts the background plasma electron. So eventually, this background electron will be encompassed by the incident beam electron. And the incident beam electron is no longer barriered by this background electron, so they can transverse to a very fast transverse motion. During this fast transverse motion process, this beam electron get very high spin polarization ratio. Yeah, I have a Hamiltonian model to detail this polarization dynamics later. So if we look at the background plasma electron motion tendency, you can find that, in this case, the background plasma electron is confined in a very, very small area. Yeah, and meanwhile, this also do multiple rebounds between each of the magnetic filaments. Now you can see this red line indicates the background plasma electron motion tendency. It do multiple rebounds. Besides the normal and abnormal filament regime, there is also another magnetic quenching regime. In the magnetic quenching regime, usually happens when we further increase the background plasma density. So in the magnetic quenching regime, the magnetic energy is still going up at the beginning stage, but once it's arrived at the saturation level, it will quickly go down. So here, the reason is that in this scenario, the electron chiral radius inside the magnetic filament is much larger than the magnetic filament scale length. So that means the magnetic filament can no longer confine the background plasma electron. So this background plasma electron just penetrates through the magnetic filament, and the transverse inhomogeneous of the longitudinal current is collapsed. So this is the reason for this magnetic filament gets kind of disappear. So let's recap our discussion. So how to get the criteria for the entering of the abnormal filament? As we mentioned that the abnormal filament occurs if the ion transverse motion is faster than the incident beam electron, which means that the ion transverse motion response time is less than the response of the beam electron time. And meanwhile, we can utilize the chiral radius of the background plasma electron and the filament scale length to determine which is the criteria of the magnetic quenching regime. So here, these three markers corresponding to three different filamentation regimes. And the shadow area plot the theoretical estimated threshold of three different regimes. Briefly, the analytical estimation corresponding well with the peak simulation results. Also, if we go to look at the detail of the electron spin polarization in the three different regimes, we can find that, of course, at the magnetic quenching regime, there is no magnetic field, so the electron spin polarization is very low. At the normal filament regime, both of the electron spin and the magnetic field growing linearly with respect to this density decrease. But a very interesting thing is that at the even lower density, the magnetic field strength is almost keep constant, but the electron spin polarization is still going up. What is the reason behind this physics? If we plot the correlation between the electron spin and the magnetic field strength, we can clearly see a different scaling between the normal filament case and the abnormal filament case. So we want to know why, which kind of mechanism resulting in the different scaling, as we pointed out here for the normal filament and abnormal filaments. So we try to understand the electron dynamics. We consider the filament A tend to coalescence with filament B, and the red dot is one electron that co-moving with the filament A. The filament A has a transverse velocity is Vs, and we consider the electron dynamics inside the filament A co-moving frame. Then the electron dynamics can be characterized by these two equations. Here, the A naught is the filament transverse motion acceleration, and this phi is the potential of the magnetic deflection for this electron. Actually, we can derive and obtain a conserved Hamiltonian. This Hamiltonian is independent of time. So follow this Hamiltonian, we can analytically derive the electron dynamics in this co-moving frame. So if we look at this electron trajectory, in fact, we kind of found two distinguishable electron dynamics. One is once this transverse motion acceleration is greater than this threshold, the electron will perform this drifting motion. This electron is kind of transverse velocity will gradually going up, but also it drift with this co-moving of this filament. In this situation, if we can derive the spin polarization ratio of this electron, you can find that the electron spin relative spin polarization ratio is on symmetry at this co-moving oscillation stage. So during this process, the electron spin get a net spin polarization accumulation. If this transverse motion, filament transverse motion is less than this threshold, actually the electron cannot, electron still co-move with this filament, but it does not have a very large transverse oscillation. So it's confined in this co-moving frame. So in this stage, the electron just perform polarization and depolarization. The eventual spin polarization ratio is not accumulate very efficient. You can see this just oscillate, but without obverse kind of accumulation for the electron spin polarization ratio. So let's take a look at the normal in the normal filament regime. We found that nearly all the electron just confined in this filament. The electron belongs to this confined electron dynamics regime. You can see this electron spin polarization ratio oscillate. It does not growing up to a very high volume. The reason is you can see this filament, it's just localized. It does not have a higher transverse motion. So in comparison, we can also take a look at this drifting electron in the drifting electron in the abnormal filament regime. Here, this red and yellow color show the electron that is the drifting electron in the abnormal filament case. In this case, you can see the electron co-moving with this magnetic filament to perform a very, very drastic transverse motion. And during this transverse motion process, the electron spin polarization ratio gets substantially enhanced during this transverse propagation stage. Yeah, and also for this blue and green color electron, this shows the confined electron in this normal filament regime. Oh, no, but here we would emphasize that even in the abnormal filament regime, this confined electron still exists. But the most important part to contribute high polarization ratio is the drifting electron in the abnormal filament regime. The below shows just a snapshot of the two representative electron trajectories for the drifting and confined electron dynamics. So now
you have 2 minutes.
Oh, sure. Last slide. So in this way, we can see that for the normal filament, the electron can only accumulate spin polarization by half of the oscillation, because another half of oscillation, the electron will start to depolarize. But for the abnormal filament regime, because after each of this oscillation, the electron can accumulate another more polarization accumulation. So in this abnormal filament regime, the spin polarization is more sharp with dependence on this magnetic field. To summarize, we have identified 3 mechanisms, maybe only 2 new mechanisms. So in the 3 different mechanisms, the electron polarization is different. This is intrinsically influenced by the different filament features. This electron spin polarization is ubiquitously take place in the plasma current filamentation. We would say that this intuitive Hamiltonian model is very important for us to understand the underlying mechanism of the electron polarization issue. Okay, that's my last slide. Thank you for your attention.
Perfect timing. Thank you. So, questions? Luis?
Yes, thank you. Thank you very much for the nice talk. I had read the paper, but it's always much nicer to read it, to see a presentation. So thank you very much. I was wondering, there are a few models, some older and some more recent, that look at the coalescing dynamics of these filaments.
Yes.
So there's a paper that I was involved with, Medvedev, long time ago, and there is a recent paper by Munizu that addresses this. Do you think this will change the picture? Your findings will change the picture of how the filaments will eventually coalesce? Because we are looking here still at relatively small scales, right? So as this evolves to longer and longer scales, do you think these more standard picture will change?
Yes, very, very good question. So actually, in this interaction, we only calculate the spin polarization after a kind of fixed time duration. Since we assume this electron could get ejected out of the plasma slab after propagate a longitudinal distance. So actually, you are right. The magnetic filaments tend to gradually growing up and gradually coalescence to become bigger and bigger. We only look at this transverse size, like 1 micron. This is based on the parameter that FACIT-2 provided with us. But if we consider further bigger transverse size, the ion motion will play an important role in this scenario after a long time propagation, even for the normal filament case. Because in the abnormal filament case, the ion already started to play a role. But in the normal filament case, as you point out, if we have larger transverse scale lengths, the ion could start to play a role to influence these filaments or even our spin polarization dynamics. Actually, maybe you are more familiar with this paper by than me is that in SLAC, they have this paper. This paper it shows that the ion motion start to play an important role to influence the magnetic coalescence and the filament merge. Yeah, I think it could be, but it's beyond our current calculation because we based on a very, very small transverse size.
Okay, thank you.
Thank you for your question. I will check out the paper you mentioned with Medvedev, right?
Yeah. I can put the references in the chat. Yes.
Okay, thank you very much.
Very interesting. Idea. Okay, thank you.
Other questions? Okay, since we are late. Okay, well, maybe I will ask a question, but after, since we are late already. It was a very nice talk, anyway.
Okay, thank you.
So, Bin, are you ready to share your screen?
Yes. Okay, I will.
So you can go ahead.
Okay.
Thank you very much. So, can you put full screen? Yeah, great.
Yeah.
Looks great. Okay. So thank you very much. So the last presentation of this morning, I don't know what time it of this session is a simple scheme for relativistic ion acceleration by Bin Liu. And so please go ahead.
Okay, thank you for introduction, and thanks to the organizer for giving me this opportunity to introduce our recent work. This talk is about ion acceleration. There have been ion acceleration has been a hot topic for more than 20 years, and there have been several mechanisms and many various methods. So why do we need a new scheme? Well, so far, laser ion acceleration is still in non-relativistic regime, and so maybe we need to look for something new. So in this talk, I will introduce a new and simple scheme for relativistic ion acceleration that is achieved by crossing two ultra-intense laser pulses in a relativistic transparent plasma. Okay, so this talk includes 3 parts. And in the first part, I will introduce the basic principle of the scheme. And in the second part, we will introduce a theoretical model to explain the simulation result. And at the end, we will do a robustness check to show that the scheme is robust. Okay, so we mainly focus on the near critical relativistic transparent regime. That's in this regime, a laser pulse, ultra intense laser pulse can propagate in the plasma, and it can push electrons at the laser front to forming called a snowplow electron layer. So at the end, that's the behind of the electron layer, there will be a snowplow field. And there are a lot of papers to address this snowplow phenomena. And so this is actually similar to the electron acceleration that's in the laser big field. But now the field is much stronger, so it's suitable for ion acceleration. And currently, we know that the laser intensity can be higher than 10 to 22 watts per square centimeter. So with this high intensity laser, it can produce a snowplow field with electric field strength higher than 1 teravolts per centimeter. So the ions happening in this field can be accelerated to GeV level in just 10 microns. But there are 2 key factors needs to be satisfied. The first one is that some ions has to be trapped in the snowplow field, and secondly, the snowplow field needs to propagate for a relatively long distance so that ions can be efficiently accelerated. So there have been several proposals in this regime, that in this near critical regime for ion acceleration, but most of them are are using like well-designed targets, like for example, like use targets with trace density protons and heavy ends, or like combined targets, or like targets with density in a narrow range. But so far, as far as I know, I haven't seen like any successful experiments with these targets. And as far as I know, these targets are still require something beyond the current technology. So we are wondering, can we further relax the target requirements? So this is our proposal that we use two laser pulses. One laser, we call it a trigger laser. So I don't know why I couldn't see my mouse. Okay, it's okay. So one laser, we call it the trigger laser. It propagates from bottom, and it creates some it pre-accelerates some ends. The acceleration mechanism is called a radial shock acceleration that we have been had been well investigated for decades. And then another laser, we call it a driving laser. It generates a snowplow field in this plasma, and the snowplow field picks up some pre-accelerated ends to accelerate them to high energy. And then this mechanism, this scheme, it works very practical, and we will show that in the following, that it's robust to laser target configuration. And it requires two laser system. Such laser system is still rare as far as I know, but it's in developing, and in the future, maybe they will be available. And also there are some proposals in QED regime, like producing positrons or gamma rays. They use like two ultra-intense laser pulses. So it can be possible in the future. So this is some 2D PIC simulations. The left figure is for laser laser pulse. A trigger laser pulse propagates from bottom, and a driving laser pulse propagates from the left. So this is the moment that the radial shock acceleration happens. That we can see some ends had been accelerated in the radial direction of the trigger laser, and this is figure B is the momentum distribution along the the axis of the driving laser. So at a later moment, we see some of the pre-accelerated ends had been trapped by the snowplow field of the driving laser, and they will be further accelerated. So this is the output N beam. It had been separated from the plasma. So at this moment, the density of this N beam is about 0.1 critical density, and the peak energy is about 2 GeV, with energy-wise is about 500 MeV. So how to model this acceleration process? So actually, for radial shock acceleration, it's quite clear, and there have been a lot of theoretical and experimental work, like 2 decades ago, and the N momentum can be estimated in this one, PS. We denoted like PS. And for the snowplow acceleration, that's driven by the driving laser. So we use N wave model to describe the acceleration process. Well, N wave is something similar to electron wave, and the electron wave, or maybe we already call it plasma wave, is something we are familiar. Actually, electron wave is always accompanied by N wave, but usually the N wave is too weak to be noticed. However, the ion wave can grow up, and when the electron wave breaks, the ion wave can be important. That happens in near critical density plasma. So this is 1D PIC simulation shows that this is ion density and ion momentum. We say something a wave-like structure propagates forward. We call it an ion wave. And in order to describe this ion wave, we ignore the electron density, and we can get differential equations for ions. And these equations can be shown analytically that in the non-relativistic limits. And we use subscript B to denote the background ends to distinguish the ends from the trapped ends. So this is the PIC simulation results, and the two green curves are our theoretical results. So they fit the simulation results as just this small region where the ends are trapped. And we can also use the model to describe the ion dynamics. So this is the phase space of the trapped ends. We have tracked several ends and also ion of the background. So we introduced the Hamiltonian. So these dots are the phase portrait of the Hamiltonian, and this black dash dots line is a separatrix. It separates ends, separates the background ends and trapped ends. So we say the theoretical model fits the simulation results quite well. And also the theoretical model can do like the minimum momentum for ion trapping and the maximum achievable momentum for the ends. And the model can also apply for like different laser plasma parameters. So we have also run simulations for different intensity of the trigger laser pulse. So we have fixed the driving laser pulse that's used before, but we change the trigger laser intensity. So we say the mechanism, the scheme works when even when the trigger laser intensity is quite low, like 2 times of 10 to 21 watts per square centimeters. So this means in this case, the trigger laser can be provided by only a 200 kilowatt laser pulse. So we can also predict the maximum ion energy. That's it fits with the simulation results. Also, this is a simulation for different initial plasma density. We say that for density range, the scheme works when the density range is higher than just three times of critical density, and this is quite good in comparison with the self-trapping case, because self-trapping happens only when the plasma density is higher than 8 times of critical density. Okay, so we will go to the third part.
You have 2 minutes.
Okay, 2 minutes. Okay. So we will show this is a PIC simulation that we show that the scheme works for linearly polarized laser pulses and hydrogen carbon plasma. That's different from the previous one. In the previous one, we have used the circularly polarized pulse and pure hydrogen plasma. So this is the final energy of the output N beam. So we say it's similar to the previous one, also like the 2 GeV level. And we have also simulations to show that the scheme also works when you choose the target to use different incidence angles, but I will skip this figure. Okay, another interesting thing is we can use a pre-expanded plasma. That's it can be expanded from like a nanowire or like a hydrogen jet. And this may be quite practical because for high power laser, we can use the pre-pulse to like expand the plasma to make it like the density distribution like this. And we have simulations that we have used the 2 laser pulses that we used in the previous simulation, but we have observed the readout that is similar. That's also 2 GeV. This is quite interesting. Maybe this figure has been featured on the cover of the PRL recently. Okay, so I would like to acknowledge my colleagues, and this is the conclusion. So I will leave it to you, and thank you for your attention.
Thank you. So again, perfect timing and great talk. So questions? Okay, I have a question while we wait for someone else. So can you go back to your model and just be a bit more specific about what you mean when you say that you forget about the electrons? And also a related question is that like when you have linear polarization, you are bound to heat more the plasma. So probably you have heating effect. And I think you put the electron temperature to 0 in your model, if I'm correct.
Yeah. So this model is developed from like this one. This one maybe we are all very familiar. So in this model we have included the equations of electrons and ions, and we show like wave solutions when both electrons and ions can be treated as fluid. But in near critical density plasma, the electrons they do not behave like fluid. They have already beyond the wave breaking limit. But in the channel, in the center of the channel, actual electrons have been expelled by the ultra intense laser pulse. So we can just ignore the electron density. So the equations of ions and the electrons, they are decoupled. So we can just show the equations of ions. This seems very unconventional maybe, but it works and it can explain the simulation result. And another question you mentioned that for linearly polarized laser pulse, so maybe there will be the heating effect. Yes, you are right. There will be the heating effect. Actually, in this simulation, we have used the density is slightly higher than that in the circularly polarized case. In this case, we use the density like 6 times of critical density. And in the previous simulation, we used just 4 times of critical density. So the heating effect mainly affects the propagating velocity of the laser pulse, but the snowball field can be produced still in the linearly polarized case. We can say that although with strong oscillation, so this scheme can still work. I hope my answer can answer the question.
So other questions? Okay, I don't see other questions. And so I think we can close the session. So it was really extremely nice. And so see you in 4 hours or something like that. I don't know, anyway, whenever the schedule continues. Yeah. And so thanks a lot, everybody, again. It was really nice.
That's it. Yeah. Thank you. Thank you also,
See you soon.
See you soon. Bye-bye.